We're going to completely demystify the hidden physics in metallurgy that keep a high-performance engine from just absolutely destroying itself. We're talking about the engine bearing. Now look, if you've ever spent time on the shop floor or turning wrenches, you already know these little shells are vital. But the engineering behind them, it is shockingly brilliant. And it all starts with what seems like an impossible contradiction.
Think about it for a second. Why on earth do we use soft metals? I'm talking about materials you can literally scratch with your own fingernail to support a hardened steel crankshaft rotating at 6,000 RPM under explosive pressure? Well, it all comes down to this core engineering philosophy: sacrificial protection. When a mechanical system inevitably faces wear or has to absorb damage, you purposely design the cheap replaceable part to yield in order to save the incredibly expensive one. The bearing is explicitly engineered to be the weakest link in the chain. It's not a manufacturing compromise. It's a highly calculated, sacrificial system.
So, here's our workshop blueprint for today. We'll start with the soft metal paradox, dive into the physics of the oil wedge, explore metallurgy and modern coatings, compare street versus track engineering, learn how to read forensic bearing failures, and finish up with some essential habits for bearing survival.
Section 1. The soft metal paradox. Keeping an engine bearing alive is fundamentally a tribological problem, not just a basic question of metallurgy. Tribology is the study of friction, wear, and lubrication between interacting surfaces. The materials we choose for a bearing have to constantly negotiate this wild, dynamic relationship with both the crankshaft journal and the engine oil itself. It's this delicate balancing act that literally changes second by second, completely depending on your engine's speed and load.
And you can really see that balancing act when you look at a typical day in the life of a bearing across its three main lubrication regimes. Step 1 is boundary lubrication. This is that brutal cold start phase where the oil film has totally collapsed and the load is being carried by actual metal-to-metal contact. Right here, the bearing's softness is the only thing preventing catastrophic seizure. Step 2 is mixed film lubrication. This is a transition zone. The oil is partially doing its job, but microscopic surface peaks of the metals are still hitting each other. And finally, Step 3, hydrodynamic lubrication. This is the goal. The shaft is fully separated by a highly pressurized wedge of oil and literally no metal touches. The crazy part? The bearing has to survive all three of these stages, often cycling through the whole sequence at every single stoplight.
Section 2. Physics of the oil wedge. Now, a lot of folks picture the engine's oil film as this uniform, perfectly even cushion surrounding the entire bearing. But actually, scratch that, that's not what happens at all. Under heavy load, the crankshaft journal is physically pushed off-center, and this offset or eccentricity creates an asymmetric, high-pressure convergent wedge pointing right in the direction of the load. This hydrodynamic action literally aquaplanes the massive steel crankshaft. It takes your standard 40 to 60 psi of oil supply pressure from the pump and dramatically multiplies it into a 3,000, 8,000 psi wedge of completely impenetrable fluid. Which brings us to this absolutely massive number, 17 million. This is the peak instantaneous PV rating. That's the unit load multiplied by surface velocity inside a high horsepower V8 screaming at 6,500 RPM. Now, typical lead tin overlays max out around 50,000. So how on earth does it survive a 17 million PV spike? Well, it's because that immense load pulse only lasts for mere microseconds. The bearing survives solely because its thermal mass absorbs that instantaneous spike and the flowing oil pulls the heat away right before the next pulse hits. In this environment, duty cycle is literally everything.
Section 3. Metallurgy and modern coatings.
Okay, let's step up to the workbench and actually compare the multi-layer composites we use to survive all this. First, you have your traditional lead tin overlays. These are super soft, around 12 to 18 Vickers hardness. That softness gives them incredible embeddability, meaning microscopic dirt and debris safely sink right into the soft metal rather than scoring your expensive crank. Then we have sputtered aluminum tin, or ALSN20. These are plasma deposited in a vacuum chamber, giving them a much higher hardness at 25 to 35 HV, which provides vastly superior fatigue resistance for high-performance builds. And finally, the cutting-edge IROX polymer overlays. These actually embed solid lubricants, like molybdenum disulfide and graphite, right into a resin matrix. They are absolute lifesavers for surviving extreme boundary lubrication during harsh cold starts.
But what about the absolute extreme end of motorsport? For that, we use DLC, or diamond-like carbon. Just look at that hardness, 1,500 to 3,000 HV. That is insanely hard. But remember our sacrificial bearing philosophy? Because of that rule, we actually apply this ultra-hard DLC exclusively to the crankshaft journal,
never the bearing shell itself. It drastically reduces friction against the soft bearing during those critical transitional lubrication phases. But it does it without sacrificing the bearing's ability to conform and yield.
Section 4. Street versus track engineering.
So here's where the engineering gets really interesting. We have to completely scale our designs based on the specific application. Take a passenger daily driver. We build those with tighter clearances and a much thicker, softer overlay. Why? Because that commuter engine needs 150,000 miles of dirt-absorbing particle embeddability to survive daily life. But an endurance race engine? Totally different beast. We run wider clearances and often completely ditch the soft overlay. In a 24-hour race, the sheer cyclic load amplitude is just punishing. An endurance engine willingly sacrifices that dirt-absorbing embeddability in exchange for the absolute maximum fatigue strength of the harder lining material underneath.
And hey, if you're building for forced induction, slapping a turbo or a supercharger on there, you are fundamentally altering the physics under the hood. That massive increase in peak cylinder pressure generates extreme heat. To keep things alive, builders actually widen the bearing clearances by about 4 to 8 10,000ths of an inch just to force more cooling oil through the gap. But here's the catch. When you widen clearances, you absolutely must strictly match your oil viscosity to maintain that critical 3,000–8,000 psi hydrodynamic wedge we talked about. If you don't adjust your viscosity for that new wider clearance, the wedge completely collapses.
Section 5. Reading forensic bearing failures.
Let's treat a blown engine like a crime scene for a minute. When you pull these metals out, their damage patterns are literally your forensic map. See heavy wiping concentrated just at the parting faces? That tells you there was insufficient crush. The bearing literally wiggled around in the bore. What about a clean wipe right in the dead center? That's classic overload fatigue. You simply exceeded the hydrodynamic film pressure. But what if you pull a shell and see uniform even wear, but with tiny particles embedded all over the entire surface? That is a textbook symptom of extended oil change intervals or severely degraded filtration. That right there isn't a mechanical failure. That's a maintenance failure.
Let's dig even deeper into the forensic evidence. If you see corrosion pitting, which looks like this rough, matte, porous texture right near the oil feed holes, your bearing was under chemical attack. This is usually caused by coolant leaks or highly acidic oil from, you guessed it, skipping oil changes. See honeycomb craters? That indicates cavitation erosion. That's when high-speed oil flow creates literal vapor bubbles that violently implode against the bearing surface. Super common in high RPM engines. And finally, spallation. This is the end game of fatigue cracking. When severe cooling failures or trapped debris create localized hotspots, microscopic subsurface cracks intersect and literal chunks of the overlay just flake right off.
Actually, let's circle back to crush for just a second, because it is absolutely vital. Bearing shells are intentionally manufactured just slightly larger than the circular bore they sit in. When you torque the connecting rod cap down, it forces an interference fit. This isn't just to keep the bearing from spinning. This crush-generated contact pressure is a non-negotiable mechanical necessity that conducts heat away from the bearing and dumps it safely into the engine block. Insufficient crush ruins that thermal contact. The bearing gets hotter, the oil film boils and breaks down, and boom, you trigger a catastrophic thermal runaway.
Section 6. Habits for bearing survival. Okay, we've covered the heavy physics and the forensics. Now let's lock in some practical, hard-earned wisdom. Here are your golden rules for daily driving. First, idle for 30 to 60 seconds before applying any real load. This gives your oil pump crucial time to transition those bearings entirely out of that brutal boundary lubrication phase. Second, strictly match your oil viscosity to your specific bearing clearance. Dumping thick, heavy racing oil into a tight clearance passenger engine actually chokes off oil delivery during cold starts. Third, maintain proper oil change intervals. You aren't just refreshing the lubrication, you are flushing out the nasty acids that cause that corrosion pitting we talked about. And fourth, and please hear me on this, never ever rev a cold engine. You are directly mechanically scoring your bearing overlay before that protective hydrodynamic wedge even has a chance to form.
Look, the engine bearing is an absolute masterclass in sacrificial engineering. It survives a terrifying environment of extreme pressure, blistering heat, and constant contamination precisely because it was designed to yield rather than resist. It does its job quietly and perfectly, right up until the basic laws of physics are ignored. So I'll leave you with this. If engine bearings are brilliantly engineered to sacrifice themselves just to save your engine, what other complex mechanical systems are you failing to protect by ignoring the underlying physics? Keep that in the back of your mind the next time you turn the key. Thanks for joining me for this explainer, and keep learning.